Okay, so we're going to change gears a little bit and talk about a different example of circular motion. And that is sort of the original example of circular motion, and that is the motion of planets. Having a lot of lag still on my thing, so I'm sorry that makes my writing a little worse than it's already bad state. Okay, so we talked when we first began talking about Newton's laws. I gave a sort of historical introduction, and we talked about Kepler's laws, and hopefully most of you or all of you were able to do the lab on orbits and just kind of refamiliarize yourself with that a little bit. But I'm going to show you quickly what the simulation from the lab looks like, and then I'm going to discuss all of that in a little bit of context. Okay, so I have this set up with the Earth going around the sun, and I have it on the 2-scale option. I had you using the model option. I'm doing the 2-scale option. And so we can really see a very elliptical orbit. This is an orbit where the planet is, it almost is going to escape from the orbit. If we would make the velocity vector a little bit bigger at sort of a key point, maybe here, it's going to keep going and never come back. Okay, so you guys hopefully experimented with that a little bit, and I want to talk about the equations that control that motion today, and we'll learn how to solve some problems. So the basic ideas in Kepler's laws. He said that the orbits are elliptical. Okay, and that's what we just saw. We saw an elliptical orbit, and you may not know from geometry class, but an ellipse is a shape that has two what are called the foci. The singular would be a focus. This is a focus, that's a focus, these are the foci. This is not supposed to look like a smiley face, but there are two foci. And Kepler actually said that the planets move around an elliptical path with the sun at one focus. And that's what we saw in that simulation I just showed you. The sun was very close to one side, and the planet, it got very slow when it was far away, and as it got close, it swooped around very quickly. And the sun actually moves a tiny bit around as the planet swoops near as well. They're both moving, but because the sun is so massive, it doesn't move very much due to the influence of the Earth. And he additionally said that in equal areas are swept out in equal amounts of time. So if this represented, let's say, a month's worth of travel, then the area, whatever area, I would say it would be something like this, where these two areas are equal, this would also have to take a month. And obviously, the planet has to move a lot faster to travel along this path than this path in the same amount of time. So qualitatively, we can say that the planets speed up when they get close to the sun and they slow down and get farther away. And you saw that in the simulation. But to actually numerically work it out, that's probably more work than it's worth doing. But we could actually sweep out, take screenshots of that picture and compute areas, and we would be able to show that as well. And finally, he said that the period squared was proportional to the radius cubed, where the radius is defined, we have a semi-major axis, which is like the long quarter axis, and the semi-minor axis, we can call these A and B, and we would just say R is equal to the average of those two numbers, which you hopefully did in your simulation. So we're going to work with the equations now, coming back to Newton's theory of gravity, which says there's a force of gravity between any two masses, and that force is proportional to the masses and inversely proportional to the distance squared, where R in this sense really would be, if here's my planet, then R is the actual distance, not the average radius. This is more of an average, radius, and this is R at its particular moment in time, okay, in Newton's equation. So if we look at this, and then we have circular motion. Now I showed you an ellipse that was not very circular, but most of the planets are almost circles, which is why everyone thought they were circles for a long time. They're very close to perfect circles. Some are a little bit more elongated than others. So if we think of the planet as moving, just in a circle with a radius r around the sun. Here's the sun, here's the planet. Then we could say net centripetal force equals m times a centripetal. And the centripetal force would be the force of gravity. But the force of gravity is not just mg. That's what we notice on Earth, because everywhere on Earth, the radius is basically the same. Imagine we're living, standing on top of a sphere. And at least I like to feel like we're on the top. We're probably on the side somewhere. So we're on top of the sphere, and no matter where we are, if we're somewhere over here, the radius is always the same. Okay? So we would have the mass of the Earth and, the mass of some object on the Earth, and all of this stuff is the same always for anybody on Earth, all of that. And we're going to show in a minute that this turns out just to be equal to the acceleration due to gravity. Okay? So according to Newton, if in orbit, we do not have just the radius of the Earth here, but some altitude, some distance above the Earth. Or if we're the Earth in orbit around the Sun, then this distance is the distance between the Earth and the Sun. So we have G, M Sun, M Earth over R squared, according to Newton. And the mass that appears on the right-hand side is the one that's moving in the circle. So that's going to be the mass of the Earth. We can cancel out the mass of the Earth, which means that if we did the same exercise for Jupiter or Venus or Mars, whatever planet we chose, its mass would be canceled out of this equation. So we have G times the mass of the Sun over the radius squared equals M. So the mass of the Earth just canceled out. So we really just have V squared over R. Now, Kepler's law doesn't talk about velocity, it talks about the period. So we need to express the velocity in terms of the period. This is the distance over the time. And the distance would be 2 pi r. Time would be the period if we go one complete revolution. So we can rewrite this equation, and the v squared we can write as 2 pi r over t and square it. And then we have to divide by one more r. So the right-hand side, I'm just going to work with the right-hand side here. It's going to be 4 pi squared r squared over t squared, and all of that is over r still. And we can cancel that r with one of those. So what we get is g m sun over r squared equals 4 pi squared r over period squared. Now, starting to get to something that looks like Kepler's law, because we have t squared and there's an r cubed. If I rearrange this, I can move the t squared to the left. And on the right, so what I'm doing is I'm moving this guy down there, and I'm moving the r squared to the top on the right. What we're going to get is 4 pi squared r cubed over g times the mass of the sun. Or in other words, just to rearrange it one more time, we have 4 pi squared over g mass of the sun times the radius cubed. Now this number is a constant for everything in orbit around the sun. That is, if we look at something in orbit around the Earth, like our moon or a satellite in orbit, then we would be putting the mass of the Earth in here instead of the mass of the sun. So this is equivalent to saying that the period squared is proportional to the radius cubed. Saying one thing is proportional to another thing is equivalent to saying it's equal to a constant times that other thing. Now, another observation of Kepler's was that that constant was for all of the planets, but the moons of Jupiter and Saturn, there were 4 moons of Jupiter and Saturn each that were visible to people on Earth with early telescopes at that time. So they had data for those as well. The 4 moons of Jupiter also obeyed this law, but with a different constant. And the 4 moons of Saturn obeyed the law with still a different constant. And Newton was the first one to understand that the reason is that if we are going to do the same calculation on Jupiter, the only thing that changes is the mass of the sun becomes the mass of Jupiter. In fact, if you look up on Google the mass of Jupiter, which is enormous, you'll find a number. That number comes from this equation. We have data on this constant for the dozens of moons of Jupiter that are visible to us now with modern telescopes. So we have numbers, we have very good data for this constant, and we use that data to find the mass of Jupiter, or to find the mass of the sun, or the mass of the Earth, for example, because the Earth has a satellite as well. But for planets that don't have a satellite, it's not as easy for us to predict their mass. Okay, so this is basically what Newton did when he was home during the plague. It actually took him a long time before he published that work, but that's when he began thinking about it. And that's what we want to work with today. So are there any questions? Dustin?
I got a little behind. What's written underneath the 4 pi squared GMS?
So this down here?
Correct.
Yeah, that says const. I kind of started writing constant. Oops. But I just kind of stopped it and put a period. So it's constant.
Thank you.
Sure. Any other questions? Okay, so let's, keeping this in mind, try a practice problem from the textbook. So this is from the college physics book, Chalmers College Physics, problem number 9.11. It says a spaceship orbits the moon at a height of 20,000 meters. So we draw the moon. The moon's happy. And then we have a spaceship in orbit. And the height is 20,000 meters. Assuming it to be subject only to the gravitational pull of the moon, find its speed and the time it takes for one orbit. So we're going to find v and the period of the orbit, the time it takes for one orbit. So of course we know that the force acting on the satellite is the force of gravity. And we can say net force equals ma, but we really only want to think about the centripetal components. And so that's going to be the force of gravity. And then the mass, we should call this ms, and this one we should call m. So this would be ms, the mass of the satellite, times v squared over r. Force of gravity would be g times the mass of the moon times the mass of the sun over r squared. Keep in mind, this S is for the satellite, not for the sun, so that's a little departure from how we did it last problem. And whatever it is, it cancels out anyway. So we want to find V. The constant G is given. Let me do it up there. This is just an experimentally, determined constant. 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So that's just a number that's on your formula sheet. So we recognize we can cancel one of these r's, and then the formula for V squared is G m moon over r. And V would just be the square root of those numbers, G times the mass of the moon over r. Now the problem goes ahead and gives us the mass of the moon and the radius of the moon. So r moon equals 1.738 times 10 to the 6 meters. And the mass of the moon is given as 7.34 times 10 to the 22 kilograms. But this radius here is the radius of the orbit. It's not the radius of the moon. It's also not the height h. What is it exactly? The radius is all the way from the center of the moon to the orbit. So that is r moon plus h. So V equals the square root of G m moon over r moon plus h. And now we can get a number for that. 6.67 times 10 to the minus 11. These problems are probably why scientific notation was invented. 7.34 times 10 to the 22. And on the bottom, we have 1.738 times 10 to the 6 plus 20,000 is 2 times 10 to the 4. So I'm just rewriting the 20,000 in scientific notation here. So the orbital velocity that I'm getting is 1,669 meters per second. Now this formula, in general, we don't want to memorize it. We want to work from Newton's laws, okay, and Newton's force of gravity. But this would be what we would get anytime we're finding the velocity of a certain orbit. We see that the velocity necessary to be in orbit really just depends on the radius of the orbit. I mean, it also depends on the mass of the planet. But for example, on the Earth, we have many, many, many satellites. And the mass, the G and the mass of the Earth are the same for all of those. So, all that really varies is the velocity and the radius. If we put it up at a certain speed, it's going to be at a certain radius. If we want it to stay at a certain radius, we have to make it have a certain speed. Okay, so that's V. How do we find the period? Well, V is 2 pi r over t. That is its distance over time. So we can just rearrange this, and we get the period is 2 pi r over v. That's going to be 2 pi times 1.738 times 10 to the 6 plus 2 times 10 to the 4. So that's my r over 1,669. So I'll move up here. The T I got was 6,619 seconds. Now, T is going to come out in seconds because we're using metric base units for everything, and the second is the metric base unit. So if I divide that by, or multiply by 1 hour over 3,600 seconds, because that's how many seconds there are in an hour, we get 1.84 hours. So that's how long it takes the satellite to make an orbit around the moon. Okay, questions? Okay, now let's go back. I made a claim. I said we've got force of gravity on Earth. We're going to have the mass of the Earth times the mass object and over the radius of the Earth squared. And I basically asserted that all of this stuff is just the G. So that this would be equal to the mass of the object times G if we're on the surface of the Earth. Let's check it out. The mass of the Earth is 5.98 times 10 to the 24 kilograms. And the radius of the Earth at the equator is 6.38 times 10 to the 6 meters. So according to this calculation, G would have to be plugging in all of these numbers, G times the mass of the Earth, which is the 5.98 times 10 to the 24, over the radius of the Earth squared. We put all that into our calculator. We get 9.799 meters per second squared. So this is where, the 9.8 number that we use, of course, that 9.8 number was first experimentally determined, and but over the surface of the Earth, the radius varies a little bit. Remember, this is 6,000 something kilometers, so it only varies in the sort of double digits of kilometers from the bottom of the ocean to the top of the tallest mountain, which is still less than 0.1%. And so G varies very little. You know, well, actually, I mean, the equator does bulge a little bit more than just the sort of the height of mountains would indicate. But nevertheless, G actually varies from about 9.78 to 9.83, depending on where on the Earth you are. But it always rounds to about 9.8. Now, if we went to Mars and we want to know what is the acceleration due to gravity on Mars or on the Moon, we would do the mass of the Moon and the radius of the Moon. So let's do that. G on the Moon, since we happen to have the numbers, that's going to be G m Moon over R Moon squared. That's 6.67 times 10 to the minus 11 times, what was that mass of the Moon? Was 7.34 times 10 to the 22. And the radius was 1.738 times 10 to the 6. So you should work that on your calculator while I'm doing it. I get 1.62 meters per second squared. Which is basically almost exactly 1/6 of the G on Earth. And if you do the same thing for Mars, you find out that the acceleration due to gravity is something 1/3 of what it is on Earth. And on Venus, it's actually close to the same as Earth, and so on. Okay, so you have a problem or two involving finding acceleration due to gravity on different, different solar system objects. Any questions? Okay, then I just have one more problem I'd like to do with orbits. And that is, we're going to find the height, above Earth for a geosynchronous orbit. Again, I apologize because it's like 30 letters behind the screen, behind what I'm writing, so I really can't see how it's looking as I'm writing. So that says geosynchronous. What does that mean? It means that the period is 1 day exactly. And this is how the majority of our satellites operate, because the idea is we want the satellite to just hover in space above our city so that we can have a satellite dish pointed right at it, and it just stays there. And that means, because the Earth revolves on its axis and we kind of rotate around and return to our same position once every day, that satellite has to do the same thing. It has to make a complete orbit once a day so that it can stay sort of just nestled in the sky in a particular position. And our telecommunication satellites all operate that way. Our spy satellites go, on, maybe 1 to 2 hour cycles and sort of roam over the globe. So we know that the force of gravity is equal to m times v squared over r. And this is going to be the mass of our satellite. So using Newton's equation, that's g times the mass of the Earth times the mass of the satellite over r squared. This is equal to the mass of the satellite. And remember that the velocity v is 2 pi r over the period. We have to square that. So we can kind of cancel out some things. The M of the satellite cancels. One of these R's cancels. And we're just kind of repeating what we did previously that gave us Kepler's law. We have 4 pi squared r squared over period squared. But this time we're trying to solve for r. So we'll move this r on the left up to the right and give us an r cubed, and we'll move this other stuff, so we're going to move this here, and we're going to move that down, and this one's going to move there. Okay, so we're doing some algebra. We're going to get t squared g me over 4 pi squared equals r cubed. So to get r, we have to take the cube root. Make sure you know how to do a cube root on your calculator. Period squared g, mass of the Earth, over 4 pi squared. So for the period, we need to convert this into seconds. So we always do that by multiplying by a ratio. We're going to have 24 hours over 1 day. That's just 1, and the days will cancel. And then we have, we want seconds, so 3,600 seconds per 1 hour. And if you don't know that, then you do it 60 minutes and then 60 seconds. And 60 times 60 is 3,600. So this gives us the period is equal to 86,400 seconds. And so that's necessary for us to plug in our numbers. Now we're going to get the cube root of 86,400 squared times 6.67 times 10 to the minus 11. It's a little hard to read there, minus 11. And then we have 5.98 times 10 to the 24. And all of that is over 4 pi squared. And what I get is R equals 4.23 times 10 to the 7 meters. But R is not actually what we were asked for. We were asked for H. Remember the picture. Here's radius of the Earth. And here is H. And this whole thing is R. And so H plus radius of the Earth equals R. So H equals R minus the radius of the Earth, which is 4.23 times 10 to the 7 minus 6.38 times 10 to the 6. So the height is 3.59 times 10 to the 7 meters. So that is the magic radius. There is basically a ring around the equator of space junk. Just, all kinds of active and inactive satellites that are all at that radius so that they have an orbital period of 1 day. So if an evil supervillain wants to really screw up the Earth, It's just going to make a big, dump truck, a big thing that just flies around and gobbles up all the stuff on that ring, and that will destroy our whole communications network. All right. So any questions? All right. That concludes our unit on gravity and circular motion. Tomorrow we will begin talking about energy, and energy is my favorite topic. So I wish we had more time to talk about it, but I'm going to be preparing for you and posting a little later today kind of a mini lab. This is not even a full-length exercise compared to our other exercises, which I hope are not too long already. But this is just a little kind of preview of energy to kind of get your mind set and ready to think about what energy is and how it behaves. And then we can dig into that in the lecture tomorrow. So if you notice from the schedule, we had a lab due today. We have this kind of very small lab due tomorrow, and then I think on Thursday we'll have a third lab. So a lot of labs this week. I am trying to get caught up on grading labs, but you guys keep making me give you contests so frequently. If you just let me skip a contest or two, I'm kidding. I know that you'd be willing. Anyway, I'm trying to get caught up on those. As you turn in corrections, those are probably the lowest priority for me to look at. So I will look at them, but I'm going to look at them after I'm caught up on, or almost current on labs. But if you have questions, about the labs, if the question is just when will it be graded, I really hope to be caught up by the end of this week on, through tomorrow's lab. I won't have the Thursday lab graded, but I'd like to get all the way caught up by Friday on the labs. So, and then I will be able to address your revisions of labs. Now, there's no time limit on the revision. You're not going to lose points or anything, so you shouldn't worry about that. It's really on me to get it done, and then if you still have corrections to make, you can just make another round of corrections. Okay, does anyone have any questions about anything in this unit or about going forward? Elise?
On this example, I'm confused where you got the number for RE. Like 6.3.
Oh, so that we just had that number on the previous example.
Oh, okay.
So I'm just kind of pulling it back from that example.
Okay, thank you.
Sure. Other questions? And by the way, you don't need to know the radius of the Earth or radius of the Moon or this G or mass of the Sun, any of those numbers. I know those numbers, but you don't need to know those numbers. They will all be provided either in the problem that you're working on or on the equation sheet on the contest. Other questions? Okay, so that's it for today. Again, like normal, stick around if you have individual questions. Otherwise, I'll see you tomorrow.